Hi, today we're going to talk about section 10.1, Properties of Exponents. And I am taking a little sigh of relief because this is the stuff I'm familiar with and I actually kind of find fun. So and also the prep for this lesson didn't take very long. So it was just lovely. All right, so properties of exponents, and can I point out we are starting chapter 10. We only have 10, 11, and 12. And there's not a lot of new stuff, mostly review in chapter 12. So I cannot believe how far we have come. All right, so give yourself a pat on the back and dig in and let's finish out the year strong. So like terms can be added and subtracted. What do I mean by like terms? Well, like terms are simply the variables and the exponents are exactly the same. And wow, that's terrible spelling right there. That is exponents. All right. So 2y plus 3y. Well, our exponent on the y, if you don't see it, is an implied 1. So the exponents are the same and the variable is exactly the same. So we can go ahead and add that, 5y. 7x squared minus 5x squared. Our exponent is 2 on the x, and the x is exactly the same. So these are like terms. So if we have 7x squares and we subtract 5x squares, we will have 2x squared. 3m squared n plus 9. Oh my goodness. You're on my computer. What on earth? 9m squared n. The variables are exactly the same, m and n, and the exponents on those variables are exactly the same. We have 2 on the m, and the exponent on the n is the implied 1. So we can add those and get 12m squared n. 6a squared plus 4b squared. Well, our exponents are the same, but our variables are not. So we cannot, these are not like terms. And then one more example, 8xy squared minus 2xy. Well, our x and y variables are the same, but our exponents on those variables are not the same. The x has a 1, which is good, but the y has a 2 on the left and a 1 on the right. So these are not like terms, and you cannot simplify them. All right, so there is a product rule, and let me just give you the product rule, and then I will explain the product rule. The product rule says that given a base of a to the m power times a to the n power equals a to the m plus n power. So why is that? If I were to have x cubed times x squared, that would equal x times x times x. All of that is for the x cubed. Then times, because of that, x squared. X times x. That x squared. That is the same as saying you could rewrite x times x times x times x times x to be x to the 5th. So it's easier just to go x to the third times x squared equals x to the 3 plus 2 equals x to the 5th. Just as a side note, remember that x times x is not 2x. That people get confused with that. And all you have to do is think logically for a second. If I put 3 in for my x, 3 times 3 equals 9. You know that. 3 times 3 equals 9. Well, 2 times 3 equals 6. So when you actually plug a value in, that can help you remember, oh, this isn't 2x. I'm not doubling my x. I'm squaring my x. So x squared is what x times x equals. All right. So that is the product rule. And there is one example. Y squared, this is example 10.1a on page 474. If I have y squared times y to the 4th, it would equal, all we're trying to do is simplifying it. Y to the 2 plus 4 equals y to the 6th. Easy peasy, right? If I have p to the 7th times p to the 4th times p to the 1st, notice, remember with algebra, you can put the variable right beside the other variable, and that is an implied multiplication. So p to the 7th times p to the 4th times p to the 1st would be p to the 7th plus 4th plus 1st power, which equals p to the 12th. We're just simplifying. And then finally, the last example for the product rule is n times m squared times n cubed equals what? Well, we have two n's, so I can go, and the numbers are being multiplied. I can add those into the first plus 3 times n squared, which equals n to the 4th times m squared. All right, the last thing to look at is the quotient rule. The quotient rule says a to the m power divided by a to the n power is going to equal a to the m minus n power. Now this one, if you don't remember it, it will simply be so easy to figure out. If you had a to the 5th divided by a to the 3rd, that would be the same as a to the 5th divided by a to the 3rd, right? And that equals a times a times a times a times a divided by a times a times a. And then those a's, 3 a's on the bottom, would cancel out 3 a's on the top, and I'd be left with a squared. Or I can simply remember this rule that I can subtract my exponents, and I can go a to the 5th divided by a cubed equals a to the 5th minus a to the a to the 5 minus 3 power a squared. And you'll see we get the same thing. All right, so some examples for this on page 475 are y to the 5th power. I'm sorry, that's y to the 6th power. Y to the 6th power divided by y squared. Oh, look at that cutie patootie. Divided by y squared equals y to the 6th minus 2 equals y to the 4th. Sample problem B is b to the 4th times c to the 8th divided by c to the 4th equals b to the 4th times c to the 8 minus 4, which equals b to the 4th times c to the 4th. Now, if I had x cubed divided by x cubed, I could rewrite that 1, right? Whenever my numerator and my denominator are the same value, the value is always, it can be simplified as 1. A number divided by itself is 1. So if ever you see that the term in the numerator is the same as the term in the denominator, go ahead and simplify it to 1. In addition, if you have a variable that is being raised to a negative power, this can be rewritten 1 over a squared. Those things are the same. So that's just a quick reminder of what the negative exponent means. All right, so we just have one quick example more to do, and we are done. C squared divided by c to the 7th equals c to the 2 minus 7, which equals c to the negative 5th. And then you'd rewrite that 1 over c to the 5th. All right, that's it. Good luck with your homework.